Okay, good afternoon, everybody. Welcome. The first thing I'm supposed to tell you is ask you if you could please switch off your cell phones. We are taping this presentation. Otherwise, even if we're not, it would be very nice if you could switch them off. Now, it is a pleasure to welcome Dr. Benjamin Santer from Lawrence Livermore National Laboratory. And this presentation, this seminar, is part of a public seminar series organized by the Keck Institute for Space Studies. And this particular one is in the context of a Keck mini program on climate and future observations. Now, last night, when I was thinking about going to the website of Dr. Santer to look at his bio, I actually went into my shelf and found out that if you want to know more about Ben Santer, you can buy The Change in the Weather, and you have an entire chapter dedicated to the important work he has done. Now, Ben got his PhD from the University of East Anglia in England at the Climate Research Unit in 1987. From then, he went to the Max Planck Institute, where he worked with Klaus Hasselmann. And since 1992, he has been at Lawrence Livermore. He's going to talk to us about the MSU Debate, the Climate Auditing, and the Freedom of Information Act. Thank you.
Thanks, Joao. Welcome. I've enjoyed my last couple of days here at Caltech. And my job today is to tell you a little morality play, or the scientific equivalent of a morality play. This is a story about science, about non-science, and about nonsense. Well, first of all, I want to give you a brief history of this so-called microwave sounding unit debate, or MSU as we call it. These are instruments that have measured the temperature of broad layers of the atmosphere from space since 1979. And this MSU debate has really occupied, some would say preoccupied, our field for well over a decade. So what is it? Why should you care about it? And in order to present this issue to you, we're going to have to get into some fairly simple statistics. There'll be a couple of equations. Please ask questions if anything is unclear to you. And then at the end of the discussion of the science, there will be some discussion of what happened after we published a paper that dealt with this microwave sounding unit debate and my encounters with the Freedom of Information Act and some of the lessons that I've learned. And I think that these lessons may have broader relevance. They're not only applicable to one individual scientist or one individual study, they have applicability to maybe to many of you in the audience too. Okay, so I'm sure that any of you could have opened up your newspaper in the last 5 or 6 years and read something like this. This is from the Los Angeles Times in 2004. I'm not picking again on James Schlesinger, who was the former Secretary of Defense, Secretary of Energy, and Director of the CIA. Again, many others have written similar things. Mr. Schlesinger wrote that satellite measurements over 35 years show no significant warming in the lower atmosphere, which is an essential part of the global warming theory. So this introduced this notion of inconvenient observations, as you might call them, killer observations that fundamentally contradicted everything we think we know about human-caused climate change. Our expectation is that as we burn fossil fuels, as levels of greenhouse gases increase in the atmosphere because of that fossil fuel burning, the lower atmosphere should warm. And these satellite measurements from microwave sounding units apparently showed cooling of the lower atmosphere, actually where we should see the maximum warming. So if these measurements were indeed correct, then this suggests that there's some fundamental problem in our understanding of how the climate system should react to human-caused increases in greenhouse gases. So let's look at this issue. How do these microwave sensors work? Well, they measure the microwave emissions of oxygen molecules. Oxygen is fairly homogeneously distributed throughout the atmosphere. And the idea is that by measuring these microwave emissions at at different frequencies, since those emissions are proportional to the temperature of broad layers of the atmosphere, you can actually retrieve the temperature of the troposphere, the temperature of the lower stratosphere, and if you're clever enough, then construct climate quality records, get estimates of changes in those temperatures over the last 30 years or so. And most of the focus of these measurements and most of the focus of the debate has been on the temperatures of the lower 7 to 8 kilometers of the atmosphere. Two groups have really been the primary protagonists in this great MSU debate. The first group is at the University of Alabama at Huntsville, John Christie and Roy Spencer. The second group is here in California at Remote Sensing Systems, a private company in Santa Rosa in California. And both groups have attempted to construct climate quality records of atmospheric temperature change from these microwave sounding unit measurements. So let's look at them. This, for example, is an estimate of the temperature change of the lower atmosphere, again, the lower 7 to 8 kilometers of the atmosphere, in blue from these microwave sounding unit measurements. And this particular record was compiled by the University of Alabama, or UAH, as I've called it up here. And this was the puzzle. The University of Alabama record suggested that the lower atmosphere in the deep tropics had cooled since 1979, whereas surface measurements from satellites, from ships of opportunity, from buoys, suggested that the tropical ocean surface had actually warmed over the same period. Now, as you can see, these overall changes are small relative to the large year-to-year fluctuations in temperature. In the tropics, we understand many of the reasons for these fluctuations. When you have large El Niños, they tend to heat the planet. You can see here, this is the large El Niño in 1982-83, one of the largest of the last century. La Niñas tend to cool things down. You also have massive volcanic eruptions like the eruption of Mount Pinatubo, which introduced some cooling after 1991. So as climatologists, we understand many of the reasons for these ups and downs in both the red curve and in the blue curve. What we did not understand, and what was a major mystery to us, was why the air above the surface should cool over multiple decades in response to estimated warming of the underlying surface. And the amazing thing in this debate was that for the longest time, only one group was involved in trying to construct this estimate of tropospheric temperature changes from these microwave measurements. But as Carl Sagan said, extraordinary claims demand extraordinary proof. And what happened was that in the late 90s, the second group in Santa Rosa, Remote Sensing Systems, looked at the same raw bits and bytes, the same raw satellite data. They independently tried to replicate the first group's results. And what you see here is their estimate from the same raw data, again, of the lower tropospheric temperature changes in the tropics. And I'll toggle between the two, and you can easily see that the sign is different. The second group is actually estimating that the lower troposphere warmed by more than the surface over this period of record. How could that possibly be? How could two groups operating from the same data get such fundamentally different results? Do we understand why? The answer is yes. It turned out that much of the reason for the differences between these two groups' estimates were related to satellite orbital drift. So not one satellite has been making these measurements continuously since 1979. They're actually measurements that were made by well over a dozen satellites that have been flying since 1979. Here you see the satellites, some of them at least, and you see here on this axis a measure of what's called the local equatorial crossing time. This is a measure of how the satellites drift over their lifetime. For example, you can see that this NOAA 11 satellite drifted in terms of the time of day at which it observed a given location on Earth's surface by over 3.5 hours over its lifetime. Now, the Earth has a large daily temperature cycle at many locations, and you'll appreciate that it makes a difference whether you're measuring at noon or you're measuring at 4 p.m. or whether you're measuring at 4 or at 7. And scientists recognized this early on and recognized that they had to account for the effects of this orbital drift in sampling Earth's daily temperature cycle. And the two groups did this in different ways. And it turned out that the first group, the Alabama group, actually made a sign error in accounting for the effects of this orbital drift on the sampling of the daily temperature cycle. This sign error was uncovered by Carl Mears and Frank Wentz at Remote Sensing Systems. All of these issues were illuminated in 3 papers published in Science in 2005. Now, the Alabama group had claimed, well, hold on, our estimate of cooling is in good agreement with estimates of cooling of the lower atmosphere inferred from weather balloons. And the weather balloon measurements are independent, therefore we must be right. The second paper by Steve Sherwood at Yale and colleagues at GFDL in Princeton, the Geophysical Fluid Dynamics Lab, was a really elegant piece of detective work. They looked at weather balloons, and weather balloons are typically launched both at midnight and at noon, and they compared the estimates of temperature change from weather balloons made at night and made at noon. What they found was that the noontime ascents didn't show warming of the lower atmosphere, but the nighttime ascents did. And they also found that these differences between the nighttime and the daytime results were coherent and grew the higher up you got into the atmosphere. And they explained this as follows. It turns out that the temperature measuring devices carried by weather balloons can be heated by direct sunlight. And when they're heated, that actually contaminates the measurement, as anyone who leaves a thermometer out in direct sunshine knows. Now, scientists recognized this very early on in the history of weather balloons, so they shielded these temperature measuring devices from direct solar heating. And over time, that shielding got better. It got more effective. And that change in the shielding over time, so the change in the instrumentation itself, if you will, imparted a spurious trend to the radiosonde data. Of course, you'd see this in the daytime stuff because those are the measurements where you have direct heating of the instrument. And since the sun isn't out heating these instruments at night, you would not see it in the nighttime measurements. It was a beautiful piece of detective work. And as far as I'm concerned, both of these groups deserve medals as big as soup plates for mapping this stuff out. Our paper then showed that when you looked at this new microwave sounding unit data set, so the curve that I showed you in black here, and compared it with climate model results, and when you looked at the newer radiosonde data sets that had been adjusted for this change over time in the effectiveness of the thermal shielding, there was no discrepancy between climate models and observations and basic theory. So we thought that this riddle had been resolved, and the first report of the U.S. Climate Change Science Program, which was presented to every member of the Senate, every member of Congress in 2006, came to the conclusion, after 2 years of studying this issue, that previously reported discrepancies between the amount of warming near the surface and higher in the atmosphere have been used to challenge the reliability of climate models and the reality of human-induced global warming. This significant discrepancy no longer exists. We all thought in 2006 that this was the end of the story, but it was not. Okay, so what happened in 2007? An astronomer at the University of Rochester, David Douglas, together with John Christie, one of the developers of the first records of atmospheric temperature change from these microwave sounding units, and a graduate student at Rochester, and Fred Singer, wrote a paper published in a Royal Meteorological Society journal, the International Journal of Climatology, in which they revisited this whole issue. What they did was they devised a statistical test to compare modeled tropospheric temperature changes with observed temperature changes. And based on the application of that test, they concluded that models and observations disagreed to a statistically significant extent. Now, it's important to note that that conclusion was not based on fundamentally new model data or observational data. That conclusion was based on analysis of basically the same model and observational data that had been used in this report, the first report of the U.S. Climate Change Science Program. So essentially, they claimed to turn this report on its head, that it was invalid, and also that the IPCC report, the report of the Intergovernmental Panel on Climate Change in 2007, which had reached a similar conclusion that there was no longer a significant discrepancy between models and data, they also claimed that the IPCC report got it wrong. So these were very serious claims, and if correct, then there was really something, some fundamental disconnect between models and data that we need to understand. Fred Singer, at the time the Douglas et al. Paper was published in 2007, produced a report that sort of mimicked the format of an IPCC report. This report was issued under the auspices of the Heartland Institute. One of its sort of banner headlines was "Nature, Not Human Activity Rules the Climate." And a centerpiece of this report was the Douglas et al. Paper, claiming that that paper proved that there really was some significant discrepancy between models and observations. Fred Singer, after publication of the Douglas et al. Paper, held a press release at the National Press Club, and this is from that press release. Douglas et al. Findings are an inconvenient truth and prove that nature rules the climate. Human-produced greenhouse gases are not responsible for global warming. So let's look at these claims. How did they arrive at that conclusion? In order to do that, we need to have a brief statistical detour, but I promise you it will be very brief. Imagine you're dealing with some tropospheric temperature time series, and the T here indicates time. This might be, in our case, time in months. In our case, we have about 20 to 30 years of data, of monthly mean data. And in the simplest model that you can develop of that time series of tropospheric temperature changes, we're going to split it up into a signal part, and we'll call that signal the response, say, to things that we do, to human-caused changes in greenhouse gases, or the response to human-caused changes in aerosols. It's sort of a catch-all for all human effects on climate, say. And this other component here is pure climate noise. Natural fluctuations like El Niños, La Niñas, it's just due to natural variability. So imagine, if you will, that we could wave our Harry Potter-like magic wand and split a time series into those two components. But of course, in the climate model world, you can look at these kind of issues of signal and noise. What you can do is take a climate model, and you can generate these tropospheric temperature time series. That's what you see here. And in that model, you can run it with your best estimates of actual historical changes in greenhouse gases, aerosols, the sun, volcanic dust. But the thing is, you can perform the same experiment many times. And in this case, this model, the Japanese model that many of you here in the audience have looked at, it was run 5 times with the same human-caused changes in greenhouse gases and all that other nice stuff, but each time starting from a slightly different initial state of the atmosphere and ocean. So each time you run the model, even though you're running it with the same greenhouse gas changes, etc., you get a slightly different sequence of El Niños and La Niñas and other modes of variability. So if you look at this first realization up here, what you can see is that, well, first of all 5 of these things show warming from 1979 through to 2000. But the size of the warming differs. This particular realization shows little warming because it happens to have a La Niña near the beginning, an El Niño near the beginning, which warms things up, a La Niña near the end, which cools. In contrast, this one here, for example, has a big La Nina which warms near the end, a big El Nino near the end, a big La Nina near the beginning, so it has a much larger warming trend. You can see that in each case, this noise differs from sequence to sequence here. But when you average over all 5 of these things, you beat down the noise, and you get a better estimate of the true warming in response to the things that you've changed. Okay, so in the model world, we can study signal and noise. We can try and separate them. And we can try and get a better estimate of this trend, which is what we're really interested in. In the real world, of course, we've only got one realization of the real world. We don't have access to parallel universes, multiple realizations of planet Earth. So we have one realization of the response, the signal, what I've called the signal, the response to greenhouse gases and all that other nice stuff, and one realization of noise. So estimating this, you know, what I called the signal component, is difficult because of all of this noise. And it turns out that you've got to account for this uncertainty in estimating the temperature changes due to human factors in any statistical test that you apply. This uncertainty in estimating the solid black line there is important. That's the end of the statistical detour. So what did Douglas et al. Actually do in comparing climate models with observations? They had a statistical test, and it looked like this. They defined a test statistic, let's call this thing D star, and this part here was the average tropospheric temperature trend. So, you know, time series like the ones I just showed you from the Japanese MRI model, they had those from many different models, actually from 19 different models from all around the world. This beast here is the average from those 19 models. This here is the observed trend, so it's what I showed you in here. This is an estimate of the observed change in temperature over, say, the last 20 years or so. And this thing here is a measure of uncertainty in this guy here, a measure of uncertainty in the multi-model average trend. How did they define that uncertainty? Basically, they define the sigma SE term as a measure of the intermodel standard deviation. So they have 19 numbers, 19 different estimates of tropospheric temperature trends from 19 models. They can calculate a standard deviation. They divided it by the square root of the number of models, and that's their measure of uncertainty. This beast, it turns out, is what statisticians often refer to as the standard error. The uncertainty in estimating a mean quantity from a finite sample of results. So let's look at that visually now. Okay, so here are 19 different models, 19 different estimates of lower tropospheric temperature trends. Here the models are identified. And this black line is the average of those 19 numbers. Okay, so it's the multi-model average of the tropospheric temperature trend in response to, say, changes in human and natural factors over the last 20 years of the 20th century. Okay, so once again, that black line corresponds to this here in their test statistic. Now, this envelope here is their sigma SE. So this is their measure of the uncertainty in the black line. Okay, so again, the sigma SE is this thing here. It's this beast here. Let's put the observations on there now and see what happens. So these are the estimates of the observed trends from this case here is from the Remote Sensing Systems group. This is from the University of Alabama group. And you can see that both of these dots, first of all, have no uncertainty associated with them. There are no error bars on them. Okay, so the assumption here is that the human-caused change in tropospheric temperature in the observations is perfectly known. And you can see that both dots are outside the error bars on the multi-model trend, which led Douglas et al. To conclude that there was a statistically significant discrepancy between the models and the observations. Now, what happens when you actually applied their test to each individual model? So you could say, okay, Well, imagine that this model here was an observational trend. What happened if I applied their test to this one here? Well, it's outside their envelope. You would deem this to be not a model, essentially, inconsistent with the multi-model average. So if you applied their test to each individual model, you would conclude that 11 of the 19 models have trends that are inconsistent with the multi-model average. Any test that rejects more than half of the population on which it is based is a weird test, okay? Which should have been, sort of quite obvious to any undergraduate level statistics student. But let's proceed. Okay, so what were the principal errors? First of all, they ignored any uncertainty in the observations. As I've showed you, when you look back at their observations, they have no error bars on them whatsoever. That was an error. That was a mistake. And the mistake is tantamount to assuming that the human-caused component of change in those time series is perfectly known. And as I showed you, there's a lot of noise, particularly in the tropics, in those time series. The human-caused component of tropospheric temperature changes is not perfectly known. Their use of this sigma SE is incorrect. Sigma SE, as I said again, in statistics, is typically called the standard error of the mean. It's used to measure how well you can estimate some mean quantity from a finite sample of results. It's not an appropriate basis for performing a statistical test to determine whether a single uncertain observed trend is consistent with some population of model results. Okay, so it became obvious that something was seriously wrong with this paper. The paper received a lot of attention after Fred Singer's presentation at the National Press Club. Fox News picked it up. It was touted as it was touted as something that really was an inconvenient truth, inconvenient observations. Climate scientists are ignoring all this kind of stuff. So we devoted some time to looking at this issue and published a paper, again, in the International Journal of Climatology that tried to illuminate some of these issues. And the key thing, again, is putting the error bars on the observed trends. And they're large. And I won't go into how you estimate the error bars. They're fairly standard ways of doing that. It turns out that it's important to account for the persistence in the time series. So if you have a time series, as I showed you, of tropospheric temperature changes, those individual measurements are correlated because of things like the El Niños and La Niñas. So you can't regard each month's measurement as an independent sample. You've got to account for that autocorrelation, as we call it, that persistence in estimating these error bars. And when you do try and put error bars on these things, they are very large and they easily overlap with the multi-model average trend. Okay. Now, someone might say, well, okay, this doesn't prove it to me. You put error bars on things, but there must be some way, Dr. Santer, of comparing their test and your test under controlled conditions. Okay? And there is. What you can do is you can use synthetic data. You can use a very simple statistical model. This is called a lag-1 autocorrelation model, lag-1 autoregressive model here. I won't go into the details, but basically it's a way of testing what they did and what we did under controlled conditions. And in this model, you can specify the size of the variability and the nature of the autocorrelation structure to mimic the observations as carefully as possible. And then you can generate many, many realizations of these synthetic time series, and by chance you can see some of them show a positive trend, some of them show a negative trend, and you can do this many thousands of times and build up some library, if you will, of synthetic time series, apply their test, apply our test, and in each case, what you can do is increase the number of models that you use in the test. So that's what we did, and these are the kind of results that you get when you do these synthetic data tests. Now, when you perform these tests, you're trying to determine whether there's a statistically significant difference in trend, in tropospheric temperature trend, between the synthetic observations and the synthetic model results. And if you perform the test thousands of times, this is the number of sort of synthetic models we're considering, then if you perform the test at what we call the stipulated 5% significance level, then 5% of the time you'd expect to find a significant difference in trends, roughly, even with random data, where you know a priori that you should only get significant differences by chance alone. And when you perform the test at the 10% level, roughly 10% of the time with random data, you should get a significant difference. And with our test, that's pretty much what you get. There's a slight bias. We understand some of the reasons for that. I can go into them later, but they're not really relevant here. The key thing is that when you apply their test, it's clear that over 3/4 of the time you apply it, even with random data where you know a priori that there's no difference in trend, you find significant differences in trend. So the only thing that was robust about their test was its ability to incorrectly reject the null hypothesis of no difference in trend. This test is like loading a die. You know, you load a die, you roll the die, you're guaranteed to get a certain result. That's what this test does. And this, you know, again, there are no shades of gray in this. This is not a difference of opinion between two groups. This kind of analysis can be done very easily in a couple of hours, and it shows fairly unambiguously that what they did was just plain wrong. Okay, so we did the testing actually in multiple ways. I won't go through all the ways that we performed the comparison of modeled and observed trends. Our bottom line results were that the Douglas et al. Claimed that all simulated temperature trends in the tropical troposphere are inconsistent with observations was incorrect. And as I mentioned, that claim was incorrect because they assumed that the observed trend was perfectly known. It's not, and because they applied this inappropriate statistical consistency test. And when you do this, you know, the statistics with appropriate tests, there is no serious discrepancy between modeled and observed trends. So we published this paper in 2008. Nature wrote a little piece in which they said, riddle resolved, this puts an end to the controversy. Well, they were wrong too. It didn't turn out that way. And this gets now into the Freedom of Information Act part of the talk. So our paper was published online in the International Journal of Climatology on October the 10th, 2008. Stephen McIntyre, who's a retired Canadian mining geologist, wrote to me by email about 10 days later requesting all the model data we had used in this paper, and I was on travel at the time and did not respond to this request. I don't check my email while I'm away on travel, which was good. Otherwise, my Hawaii trip would not have been as pleasant. I wrote back, I gather your intent is to audit the findings of our recently published paper in the International Journal of Climatology. Mr. McIntyre runs a blog called climateaudit.com. You are, of course, free to do so. I note that both the gridded model and observational data sets used in our paper are freely available to researchers. You should have no problem in accessing exactly the same model and observational data sets that we employed. I should point out that the model data used in our paper are now in frequent use by over 2,500 researchers around the world as part of the so-called IPCC CMIP3 database. So there's no question that we were privy to information that was not accessible to Mr. McIntyre. The same applies to the observational data. But this was not sufficient for Mr. McIntyre. He made a request to NOAA, the National Oceanic and Atmospheric Administration, under the Freedom of Information Act, requesting a copy of the following NOAA records be provided to me: any monthly time series of output from any of the 47 climate models. I'm not quite sure where he got 47 climate models. We only use 19. Any correspondence concerning these monthly time series, et cetera, et cetera. Mr. McIntyre made this request to NOAA because I had a number of NOAA co-authors on the paper, and he had some experience with submission of Freedom of Information Act requests to NOAA. He had done that numerous times in the past. NOAA turned him turned him down and said that they did not have the data and they did not have any correspondence related to the data. He thereupon tried a second Freedom of Information Act request to the Department of Energy, who actually are the people who fund my research at Lawrence Livermore National Lab. This was quite a difficult time for me. When this request arrived, I received notification from the lawyers at the Department of Energy. They said, basically, please comply with this request. Your choice as a researcher is either to comply with the request or to fight it legally. And that could get very nasty. That could take a lot of time, as we've seen in past encounters between Mr. McIntyre and other scientists, most notably Mike Mann. That encounter ended up in Congress and ended up in the courts. So what I decided to do in the end was to release not the raw model output. That was already released, like I said. That was already available. I released all the synthetic microwave sounding unit temperatures that I had computed from the raw data. Not just the information that Mr. McIntyre requested, but actually everything that I had done, and made it available to the entire community. It's on our website. You can go get it. Anyone can do anything with these synthetic microwave sounding unit temperatures that I've calculated. But you know, this request raises some really important issues here. One issue is, well, why did he make this request? Couldn't he just calculate synthetic microwave temperatures from climate model data on his own? Why didn't he do that? Because the algorithms used for calculating those synthetic MSU temperatures are freely available. They're out there in the published literature. If he had wanted to, he could have tried, starting from the raw data available to anyone, to calculate these synthetic MSU temperatures. And you know, the first question really is, did we screw up the calculation of synthetic MSU temperatures? Mr. McIntyre could easily have seen that we didn't, and actually our synthetic microwave unit temperatures were very, very similar to those of Douglas et al. They had published their results. They had started from the same raw data that we had started from. They had independently derived these synthetic MSU temperatures. Their results and our results were very, very similar. The bone of contention was always the statistical test, not whether there had been errors in the calculation of these synthetic MSU temperatures. So, you know, the second question raised by this request was really, did we apply appropriate statistical tests? I think I've showed you that you can adjudicate that question. You can look at what Douglas et al. Did, what we did. You can see that their test fails. It does not perform as it should with random data. The more important question is, as scientists, are we required to provide auditors with information about every step of what we do? So if scientist B wants to replicate scientist A's result, is it sufficient for scientist B to have access to the raw data, to have access to information about how scientist A actually calculated some quantity of interest, or does scientist B have access to everything that scientist A did? So computer programs, how to run the computer codes, email correspondence, results of all intermediate calculations. This is the type of thing that McIntyre was requesting and has requested in the past and will request in future. And that's unclear. It's unclear whether some auditor can come to you and say, I want everything that you've done, because you were funded by the federal government. This whole thing got very nasty. I'm just showing you here an excerpt of some of the postings on Mr. McIntyre's blog when I initially refused to provide these synthetic MSU temperatures. And you know, there are people saying, we're going to put Santer in jail and we're going to submit all kinds of Freedom of Information Act requests and see what kind of dirt we can turn up. And on the basis of this, nasty things happen. People send you really the most vicious kind of hate mail. One highly placed Department of Energy official, who will remain unnamed, read this blog and thereupon wrote to the director of Lawrence Livermore National Lab, claiming that I was bringing the good reputation of Livermore Lab into disrepute. I'm sure he hadn't read Douglas et al. I'm sure he hadn't read our scientific paper. So this was very frustrating to have wasted, as I felt, many months of my life dealing with the response to a paper that should never have been published, and then having to deal with the Freedom of Information Act as well. So, as I said at the beginning, this is a story about science, non-science, and nonsense. The non-science in this case, I think, is what Douglas et al. Did. They did not behave like normal scientists do. They got a result they liked. They got that result with essentially the same model and observational data that others had used. They claimed to turn previous conclusions on their head. They never asked, was our test appropriate? Why do we get something that's fundamentally different from all those who've gone before us? They didn't ask that at all. That's why I call that non-science. And then I think there's the real nonsense about the Freedom of Information Act, because the important issue, really, the crux of the debate here, is the appropriateness of the statistical tests. And Mr. McIntyre could have looked at that without any climate model data, without any observational data, just using synthetic data, as we had done. He could have easily determined within a couple of hours that the Douglas et al. Statistical test, robust statistical test, was fundamentally flawed. So, again, I think in science, the key thing is reproducibility. Another scientist should have all the tools necessary in order to reproduce your results. That's important. I believe Mr. McIntyre did have access to all the tools, to all the data necessary to independently replicate our results. But that's also a lot of work, and he didn't want to do that work. That's my interpretation of the Freedom of Information Act request. These requests have not only been used against me, they've been used against numerous other researchers. My colleague Phil Jones at the Climatic Research Unit in the UK is now on double digits in terms of Freedom of Information Act requests. These things are very onerous to deal with. They're time-consuming. They're upsetting. They prevent you from doing the job that you're actually paid to do. In one case, they've led to congressional investigation of a colleague. And if unconstrained, because you don't have to give any cause for these requests, you can just submit as many as you want. You don't have to say why you want them. You just submit them, and the lawyers send them to you, and you have to deal with them. And the auditing, in my opinion, that Mr. McIntyre engages in is asymmetric. He only audits studies that claim to show a human effect on climate. I believe that this type of behavior really does send a chilling message to young scientists in particular. I've had a number of young colleagues come to me and say, gee, why would I want to get involved with the MSU debate? Why would I possibly want to do this? If there's the possibility that I publish a paper and I could spend a long time dealing with Freedom of Information Act requests. That's fundamentally wrong, I think. It would be very sad for people to be scared off research in these kind of areas because of fear. Another concern is that the Freedom of Information Act is not handled uniformly across agencies. DOE, NOAA, NASA have different exclusion criteria, different things that are and are not fair game under Freedom of Information Act requests. It's very confusing. I really think that there's a danger here inherent in all of this, that the Freedom of Information Act can be used to prevent us from doing our work, and that what is and what is not fair game needs to be clarified there. So I'd be glad to answer any questions I can about this morality play. I've tried at the end here to give a brief timeline of the history of the great MSU debate, and just wanted to point out that the theory of microwave absorption by oxygen and how one might measure atmospheric temperature using these emissions goes back 40 years, well over 40, 50 years now. It's, recently, as I said, this debate has consumed our community. I hope it's over now, but I've said that many times in the past and been wrong. Thank you. Yes, sir.
Have you gotten any response from Douglas or Santer on your 2008 paper? Have they sort of come back along to agree with your analysis?
No, I have not received any response from Douglas and from Singer. John Christie has provided some response. He said that there was no statistical mistake in Douglas et al. And that the findings of Douglas et al. Still stand. Yes?
You talked about, in one of your last slides, you mentioned intellectual property issues as being one of the issues raised by the Freedom of Information Act. Are you talking specifically about the software used to compute model data, or are you talking about other things besides the software?
Well, let me try and explain again. So, modeling groups around the world performed experiments in support of the fourth assessment report of the Intergovernmental Panel on Climate Change. All that model data is archived at Livermore, where I work. We provide that data to the national and international community free of charge. Don't have to do anything, don't have to sign anything. Anyone can use that data, as long as they, I believe there's the stipulation that you don't actually profit. You don't try and sell the data in any way, shape, or form. Now, what we did is we used that raw data, as Douglas et al. Did, and in order to facilitate the comparison to observed satellite measurements, these microwave sounding unit measurements, we calculated what you might call synthetic microwave temperatures from the model data. Essentially, you look at the model as a satellite might see it and try and calculate something that facilitates the comparison with the real observations. That's standard. The techniques used for doing that are very simple. They've been published. They're available. Like I said, Douglas et al. Actually did that themselves, and they did not say, give us a Freedom of Information Act request and say we want your data here. They did it themselves. What I'm saying is that it's unclear whether value-added products like that, some intermediate product that you've calculated from raw data, what's the status of that? Is that your own intellectual property? We use that synthetic microwave sounding unit data, say, in proposals. We're actually trying to get funding. Are we required to release that data to anyone who requests it? Are we required to release all codes that we develop to do any sort of diagnosis of models to anyone who asks, regardless of their bona fides? I don't know the answer to those questions. What I did in the end was say, I'm not going to fight with this guy and get embroiled in some legal struggle. I'm a scientist. I want to do science. I'm actually going to release everything that I've done, all the synthetic microwave sounding unit temperatures I've calculated from model data, and make it freely available not only to Mr. McIntyre, but to anyone in the world. But other colleagues say, and other people here in the audience, invest tremendous amount of their scientific career in developing innovative diagnostics, things used for evaluating climate models. Now, if that work was funded by the federal government, can someone come along and say, that's mine? It was funded by NSF or NASA or NOAA, and you have no exclusive right to it. Even though you may be planning to use that for future research, future papers, it's not yours. I don't know the answer to that question.
I work in the biology department on the genome database, morebase.org and Biokinetic, so I don't have a very deep familiar with what you do, but I have a fair amount of familiarity with computational biology. Consistently, I found it's a lot easier to deal with issues when the software used to compute data for a paper is available. It's just a lot easier to get things done. Because, in principle, yeah, I can go ahead and write my own code from scratch. I'd like to think I'm smart, but I'm not going to rewrite a gene pack from scratch. I don't have years. And obviously, when people use the law maliciously, that's horrible. And then comments like what you've gotten are horrible. I'm not a lawyer either. But I wonder if, like, in general, the issue of software, where you publish a paper and you say in your method section that you used a piece of software to derive the thing you're saying in the paper, I am sort of wondering what the general opinion of your field is on making that stuff open source versus closed source. Because in biology, it's just a lot easier to get things done as open source.
That's a great question. I can tell you a little bit about what's happened in the past, in terms of Freedom of Information Act requests submitted to other colleagues, where provision of the software has not been sufficient. One has also been asked to provide information about how to use the software, to provide the data in a certain format that is palatable to the requester. These things can get very, very onerous, and they can be like a black hole. You can spend a long time dealing with these requests. Again, in my case here, the thing that was so absurd was that the guy didn't actually need any data at all in order to determine whether Douglas et al. Were right or we were right. He didn't need data to do that. Yes?
It's interesting that you raise this as an intellectual property issue. What McIntyre gives you is something that's actually very common in intellectual property law. I think there's like a term for it that's slipping my mind at the moment. But it's basically where you say that you patented something, and someone comes up with an actual product based on a fairly similar patent. But your patent is vague, but the people who developed the product have actually sort of expanded the patent because they actually developed the product. They know what they actually have to patent. However, you go to a jurisdiction and say, there's one in Texas, I think that's especially favorable to this. You go to that jurisdiction and some judge will give you an injunction against the other company that is actually selling the product. And that company will have to spend large amount of legal fees and lots of lost time for the people who actually develop the product, going through all the history of patent documentation. Basically, what they're trying to do is to this is used by a larger company to drive the company that's actually selling the product out of business. The only remedy for this, apparently, is that there are people who specialize in intellectual property law. There's sort of an intellectual property law bar. And then there are lots of amateurs who figured out jurisdiction shopping and they're sort of flying by night on this. But the actual respectable intellectual property bar won't have anything to do with them. And in fact, they're trying to get ethics rules changed at the Grand Bar Association level, American Bar Association level, in order to stop this practice. I think you're right to say, yeah, the Freedom of Information Act regulations on the term level of federal administrative law have to be streamlined and very carefully reviewed, because what you got into is just a mess.
Yeah, again, if unconstrained, if no limits were set on this, someone could just submit request after request after request. Not just for information that I produce, but for information that any of you in the audience produce. And the fact that you don't have to give cause, you don't have to justify why you want it. You just have to say, I want it. It was federally funded. That's very troubling to me. And I think as scientists, we need to be in control of our own scientific destiny. I've spent 10 years of my scientific career responding to others and responding to what I judge to be poor science on the MSU issue. I don't want to do that anymore. I don't want to be reactive. I want to be in control of my own scientific destiny to say, these are the issues I want to work on. I don't want to have those issues dictated to me by a poor paper that should never have been published by David Douglas or Fred Singer or someone else. And it's very difficult then to adhere to that kind of, I want to be in control of my own destiny principle when people start hitting you with Freedom of Information Act requests. So it's tricky. I don't know the answer here. All I'm saying is be careful. I have heard that if you delete emails after completing work on a paper, then you cannot be held in any way responsible for deleting those emails. Unless, of course, you have knowledge of a Freedom of Information Act request. If you have knowledge of a request, then you can't delete stuff related to the paper. But it's unclear whether emails, for example, constitute part of the deliberative process, as some people call it, and are fair game or aren't fair game. The legal issues are murky here. I agree completely. They do need clarification. I just don't want to be the guy who clarifies them. Yes?
Is there a mechanism for public cost recovery in the case of disingenuous use of FOIA? When the public's damages are not clear? You can't say victims of Katrina or victims of station fire versus McIntyre because it's not, the damages aren't clearly linked.
I don't know the answer to that question. I believe there is some provision under the Freedom of Information Act for charging the requester for excessive requests. So my understanding is that many agencies require you to estimate the amount of time that it will take you to comply with a request, and you can impose some charges then if it's going to take you an inordinate amount of time. I didn't do that. Again, in a sense, I didn't really comply with his request. I decided to make the data available to the entire world. I did not provide the emails as requested, and I'm still waiting to hear what's going to happen on that one. But yeah, recovery of some of the time spent dealing with these kind of things, that would be great if that were possible.
Just curious, do you have a counter that says how many times what you released on the website has been downloaded? Is it only been downloaded by McIntyre, or is it downloaded 1,000 times?
I don't know. I could find out the answer to that question. I haven't looked. I think we do have a counter. It should be possible to determine how many people have downloaded that data. And, again, I think speaking for myself, and I'm sure for many of the people in the audience, we have no problem releasing data to other scientists for bona fide research. But if someone, is writing all this stuff on a blog, and if their intent is not really to do bona fide scientific research, but to do something else, I feel much more uncomfortable about releasing everything that I've done. I think this was a reasonable compromise. People who want to use the data can. Hopefully good science will be done with it. But for us now, at our organization, it does raise important questions about the future. The fifth assessment report of the IPCC will appear in 2013. We'll be deeply involved with that. Our goal is not only, once again, to serve climate model information to the national and international community, but also to calculate these kind of value-added products. And we have to decide whether we're going to make them available to anyone, plus all the codes that we use to generate these things. Again, some people have invested a lot of their careers in the development of software tools to produce value-added data, and should we be required to make all that available to anyone? I don't know.
Now, is it correct to say that it's the value-added data which is likely to be more useful in the policy implementation of that in 213?
Probably not. I think the value-added data is more useful for comparing models with observations and making judgments about the relative performance of different models. I'm not sure whether the value-added data will be as important in the policy arena. Yes?
Let me take a slightly different tack, because I think we all know that replication is part of the scientific process. And if McIntyre was a legitimate scientist and said, I tried to duplicate your data and I can't get the same result, let's open up our books and we got to compare some of these intermediate results. We got to compare our
Sure.
programs, find out why we disagree. That seems like that's 100% legitimate. And you got to roll up your sleeves and really find out what the discrepancies are to get a different answer.
I agree.
And I think if you're going to try to, if the FOIA people are going to say, well, this guy's legitimate and this guy isn't, that's really going to get into a murky area. How are you going to judge that?
I agree, but that's not the way things worked, where he said, I really want to replicate your intermediate calculations here and understand whether they're correct. That's not the way things worked in this case. The way things worked was you better provide this data, and I felt that it was more in the nature of an ultimatum rather than an attempt to do things collegially. And again, as I said, the curious thing here is that Douglas et al. Had already audited us. They had already independently used the same raw climate model data, and they had calculated these synthetic MSU temperatures. And their results were very, very similar to results that we had published in 2006 in the first report of the U.S. Climate Change Science Program. So that portion of the thing had already been independently audited. That's the bizarre thing here. The difference of opinion was in terms of the appropriateness of the two group statistical tests, not whether the calculation of the synthetic MSU temperatures had been done correctly.
One more question? Just to bring it back to your case study, was the MSU debate resolved by the Alabama group releasing code to the California group who found a sign error? And was that an important part of resolving that the code had to be released at some stage? Or what?
The Alabama group never released their code. To my knowledge, that code has been requested on a number of occasions. They've never released the code that they use to generate synthetic MSU temperatures to other researchers. They have certainly not released it to the remote sensing systems guys.
What was the sign error from?
The sign error was found when the second group tried to replicate the first group's result, and they both agreed that satellite drift and sampling the diurnal cycle was important. And all of us, the first group, the second group, me, and others, were part of this first climate change science program report, which I've mentioned. And in the process of working on that report, it became clear that we really had to understand why these two groups differed, why that black line and that blue line differed so radically. And this was really the only plausible explanation for it. So at one meeting, we sat the two groups down, and how do you correct for satellite drift, and how do we correct? And the only explanation was that the first group had an algebraic error. And Carl Mears put the math up on the board and said, this is the only way I can get the result that you've obtained. Is this the way you do it? And it turned out that was the way they did it. They did have an algebraic error in their adjustment for satellite drift and sampling the daily temperature cycle, which they admitted in 2005 in Science.
So it sounds like the process worked.
The process worked, but even after they admitted it, the expectation was that they would convert that cooling trend to a substantial warming trend based on this effect. But that didn't happen. The trend increased minimally. It did increase, at least the sign is now warming, but there's still an outlier, and because they have not released the code, we do not have full understanding of how they actually adjust, how they do it in practice for satellite drift and sampling the diurnal temperature cycle. So yeah, again, in some, it's tricky, isn't it? I mean, I'm a big fan of releasing code in order to improve understanding, but in cases when those kind of requests are frivolous, I don't know whether I'm such a big fan of releasing everything that you've done.
Before thanking our speaker again for an excellent presentation, I would like to remind you that there are cookies and coffee by the Lauritsen after the oak tree. So Jerome, meet again there in a couple of minutes. And thank you very much.
Thank you.